Plastic is found all around us and plays a key role in our daily lives. Yet as the demand for plastic has increased, its environmental impact has also grown. As research scientists here in the Williams Group at the University of Oxford, we aim to tackle this problem. We take into account both the production of plastic materials as well as their inevitable disposal, aiming to make more environmentally sustainable products which can be easily recycled.
Plastics are made up of polymers, which are long chains of repeating molecules. These are normally sourced from petrochemicals, which are derived from oil refining. Our group uses carbon dioxide as one of the repeat units. One advantage is that we can replace the fossil fuel-derived chemicals, which are often used to make the polymers. By using carbon dioxide, greenhouse gas emissions from our polymer production are 3 times lower than materials used today.
Our product can be processed into plastics, foams, adhesives, and resins, which are then used to make the materials you use in your everyday life, such as mattress foams, car seats, the soles of running shoes, and in glues. A polycarbonate is made up of repeating patterns of epoxide, shown in blue, and carbon dioxide units, shown in red. We can identify and monitor the production of polycarbonates using infrared or IR spectroscopy.
The first technique allows samples containing the plastic to be identified. Here, a solid sample is placed over the IR detector and compressed down. A beam of infrared light is passed through a crystal such that it reflects off the internal surface in contact with the sample. As the beam exits the crystal, it is collected by a detector, which converts it to the spectrum we observe.
In the IR spectrum, there is a high-intensity absorption that arises from the vibration, stretching and compression of the carbon-oxygen double bond, whose frequency of vibration falls within the infrared region and so is detectable by IR spectroscopy.
The second instrument is the in situ React-IR. This instrument allows us to monitor the polymerization process while it is happening.
The React-IR consists of the main body. The main body then connects via a semi-flexible tube filled with mirrors. The mirrors reflect the IR beam to and from the sample, which is in contact with the probe when this is placed into the reaction vessel.
Under a constant flow of CO2 over our system, the red cap is quickly removed and replaced by the probe. The flow of carbon dioxide protects the mixture from being exposed to air and provides the source of carbon dioxide for the reaction. Once the system is closed, the probe is adjusted to the level of the solution, allowing it to touch the mixture. The Schlenk tube is placed inside an oil bath, already at the polymerization temperature.
Once ready, we press start and measuring commences.
We are following the formation of a carbonyl group. As the amount of polymer increases, so does the concentration. This leads to an increasing peak intensity, thus allowing us to monitor the reaction in real time. The software combines the 2D spectra to form a 3D spectrum of intensity against wavelength and time. A thin slice of this 3D spectrum is used to create our 2D graph of intensity over time. We can see that a polymer has formed, as the solution is more viscous than it was at the beginning. We obtain our final polymer by precipitation. We add the mixture into a beaker with methanol, resulting in a white powder. Our team are working on novel applications and uses for these carbon dioxide containing polymers, as well as sourcing monomers from renewable sources. In the future, we hope there will be many more materials whose life cycles are based on sustainability and reducing greenhouse gas emissions.